this time, because this is new material and it's really, really exciting stuff. All right, section 15.2, heterocyclic amines. Heterocycles are cyclic compounds that have at least one nitrogen in the ring. And it says here that many are physiologically active and many are critical in biochemistry. And if you were to go on something like Wikipedia, which is a perfectly legitimate source for, looking at, I just saw your yeah. If you were to look at Wikipedia and look up the structures of any kind of marketed drug, whether it's Vioxx or Singulair or Avapril, whatever, anything, whatever you were to look at, you'll see that most marketed drugs, Xanax, Rivotril, anyhow, virtually all of them contain a heterocycle. So almost all of them have a heterocycle in there. You do not have to memorize all of the heterocycles that are on here. The ones that I think you should be responsible for are pyridine, okay, pyridine. And if you're really interested in pursuing biochemistry later on in your career, I would recommend memorizing the rest of them. But if we have an aromatic compound like benzene, I got pyridine on the brain. Anyhow, if we have a benzene ring, okay, so if we just insert a nitrogen in there, replace one of those carbons with a nitrogen, we end up with what's called a pyridine. And pyridine is a base. Pyridine is a basic compound, so we'll put here that pyridine is also a base. And if you've ever looked at the structures of nucleotides or nucleosides or DNA, you've probably seen some of these other bases before, like imidazole and pyrrole and pyrimidine. Here are some other examples of heterocyclic amines, and these ones have more than one ring. For example, indole and purine. I worked in indoles for a number of years. We used to have a saying in the lab, you're not a real chemist until you've done indole chemistry, which is very complex. And purine is also a nitrogenous base found in DNA and RNA. And it says here that fused ring structures share two carbon atoms in common. So when we have two rings, like in indole or in purine, we call them fused rings because they share a couple of carbons. All right. And then this big ring down here, which looks kind of intimidating, this big thing down here, this is called a porphyrin ring, and this is found in hemoglobin and myoglobin. And if you've ever studied biology before, you might have even seen this before, and you might know that in hemoglobin, the metal ion that's complexed or held inside that porphyrin ring is an iron cation that's in there, which hangs on to an oxygen. We'll talk about that more later on in the class. These are some examples of heterocyclic amines that are called alkaloids. Alkaloids just mean naturally occurring compounds that contain nitrogen. So you're all aware that cocaine is a completely naturally occurring compound. It's found in the coca plant or in the leaves of the coca plant. So here's the structure of cocaine. And if you look at the nitrogen in cocaine, when cocaine is isolated from the plant, from the leaves, it comes out as this, which is a free base, right? So cocaine is a base. You can see it's a tertiary amine, and amines are basic. Okay, well, what happens is, what they do is they take that amine and they treat it with an acid in order to form a salt. So they actually take it and they form a salt like this, a hydrochloride salt. And so when you form a salt, I told you earlier on that salts usually have very high melting and boiling points. And so the salt is actually a solid. So when you see people in a movie and they're cutting up cocaine powder on a mirror with a razor blade, and then they're snorting that with a dollar bill, what they're actually snorting is the hydrochloride salt. Because when it hits the nasal passages are aqueous. and the salt dissolves in the aqueous passages or the membranes of the olfactory system, I guess, and then it gets absorbed into the bloodstream and crosses the blood-brain barrier and gives people a high. But what you can do with cocaine is you can take cocaine and you can treat it with a base. Okay, so you can take cocaine and treat it with a base like sodium bicarbonate, which is baking soda, and then you end up removing this proton. Okay, you remove that and you convert the salt back into what? Back into the free base. Okay, so let me just let me put my salt back. Okay, I'll put it back here for you. So I take this and I convert it into the free base, and the free base, okay, where was I? The free base, what happens is it makes an oil, and that oil will harden over time, and that is what crack cocaine is. So when they take the salt, treat it with a base, okay, you generate crack cocaine. And crack cocaine, the name crack, I'm not sure where it comes from. It either comes from the sound that it makes when it's hardening, when the oil is hardening, or it comes from the sound that it makes when they smoke the crack rocks. But when they make crack, again, that free base, so the original structure of cocaine, that can cross the blood-brain barrier in seconds, and you can become addicted very quickly to crack cocaine. Anyhow, another cool example. Oops, I didn't mean to do that. Where was I? Oh, darn. This where I was? Fiddlesticks. Hold on. It's just I wanted to show you the structure of heroin. Anyhow, hopefully you can see this. It's kind of hard to see. It's cut off a little bit, but you could look in the textbook maybe simultaneously because this comes from our textbook. But, you know, the next time you get some kind of crazy email from a relative that says something like, you know, I don't know, what's something ridiculous that you hear on the internet, like chocolate pudding, you know, made by Hunt's is one, you know, just crazy stuff, like 1 molecule away from plastic. It's like, okay, all right, I guess my DNA is pretty close to that of a cucumber too, you know, but I'm not a cucumber. Anyhow, but if you look at the structures of morphine, now that you've studied organic chemistry, morphine, codeine, and heroin, you look at the difference. They share all of this in common. All of this is in common between morphine, codeine, and heroin. The only difference are these, son of a gun, these little R groups. Where the hell was I? Yeah, these little R groups on the side, which I'm trying to show you. Hopefully you can see them now, okay? So it's just these little R groups that change from either being 2 protons in morphine, a hydrogen and a methyl group in codeine, which is used in codeine cough syrups. And then if you change them to 2 acetyl groups, you get heroin. And an acetyl group is simply this, okay? It's nothing more than a carbonyl and a methyl group. So it's not that big a change, okay? So the way I would explain this to somebody on the street when people ask me, like, what's the difference? I try to explain to somebody, well, codeine that is found in cough syrup that you can buy over the counter, the only difference between that and heroin, let's say you had 2 Ford Fiestas, or maybe I'll pick a car that's more popular. I don't know. What's a car? I've never bought it. I haven't bought a new car in years. Let's say a Toyota Tundra. You have 2 Toyota Tundras. One's got, you know, brown paint and one's got white paint. That's about the difference, right? Most of it is identical. There's only a very small difference. So you have to take these things with a grain of salt, no pun intended, when people say, oh, this is, you know, we're eating, you know, something that's so dangerous or whatever. Okay. Another example is, what else could we take a look at here? B12, it's got a nitrogen in it. Oh, here's another one, LSD. So you've probably all heard of lysergic acid. So LSD, you can see that it's got an indole ring here, and it's got a nitrogen in the ring here. Basically, anything that crosses the blood-brain barrier, here's nicotine, which has got 2 nitrogens. Anything that can cross the blood-brain barrier will have a nitrogen in it, okay? Always. They'll always have some kind of aliphatic or aromatic portion, and will always have a nitrogen in there. All right. Well, now let's switch gears and take a look at section 15.3, which deals with amides. And amides are going to be very important when we look at proteins and enzymes later on in this class. So in order for you to understand what's called primary, secondary, and tertiary structure and quaternary structure of proteins, you have to have some kind of grasp of amides. And we talked about amides earlier on in the class a little bit when we discussed functional groups. And we said you have to know the difference between an amine, which is simply something like this. This would be a primary amine. But if we have a carbonyl adjacent to that NH2, then this is called an amide. Sometimes people pronounce it an amide. If you're British, they call it an amide. Anyhow, so it says here, amides are formed in a reaction between a carboxylic acid derivative and an amine or ammonia. And the amide bond is the bond formed between the carbonyl group of the carboxylic acid and the amino group from the amine or ammonia. Let me show you exactly which bond is the amide bond, and I'm sure you've got it figured out anyway, but the amide bond is this bond right here. It's this bond. It's the bond that was formed between what? The part from the carboxylic acid, all this blue portion over here, and the part that came from an amine. So an amide bond. And when I first started working in big pharma, I remember I first started working with the guy. He said, well, how many ways are there to make amide bonds? And I was like, I don't know. He said, oh, there's hundreds of ways. So finding new ways to make amide bonds used to be, it might still be, I'm not sure, but it used to be a very good business to be in, okay? Finding a new way for chemists to make amide bonds. Anyhow, it says here that most amides are in fact solids at room temperature due to internal hydrogen bonding. And I need you to memorize this part here, that amides are not bases, okay? And the reason why amides are not bases can be shown by these resonance structures down here. But I don't like these resonance structures, so I'm going to draw my own, which will be a little bit prettier. So what they're trying to show here is, let me see, if I draw, and I'm going to start with a primary amide. So if I draw an amide, I have two lone pairs on the oxygen. Oxygen always has two bonds and two lone pairs, just like in water. The nitrogen has three bonds and one lone pair. But what happens is, the lone pair on the nitrogen atom can participate in resonance. Resonance, okay? And let me draw the resonance arrows for you. That's what's, represented here, but I'll make it look a lot better, okay? So what happens is you can take those two electrons and form a new bond here, so that you'll have a double bond, but then that would give the carbon 1, 2, 3, 4, 5 bonds, and you can't have that. So what happens is the pi bond breaks and the electrons go up on the oxygen like this. So let's draw what the other resonance contributor would look like. And I'll show you. It would look something like this, where we have one bond to oxygen. And now the oxygen would have a negative charge, and we would have a double bond to the nitrogen. And the nitrogen would have a positive charge. Right? If we think about this. If we're starting with something that's neutral, we have to end up with something that's neutral. Okay? So my point is this. Pay attention. If you're drifting off, everybody wake up just for a second, because this is crucial. When we talk about amines, like ammonia, okay, if we have an amine, the nitrogen on here, the lone pair on the nitrogen, that lone pair isn't going anywhere. It is just sitting there on top of that nitrogen, and we call that being localized. What does it mean to be localized? You're stuck in one place, right? And a base is something that can donate electrons. So I'll write that up here. So bases donate electrons, okay? Electrons. Okay, so an amine, the electrons are just sitting there like, open for business, I'm ready. Somebody give me a proton, okay? So these are bases. What's the problem with the lone pair on an amide? Is that this lone pair that I'm highlighting in blue right here, okay? That lone pair is not localized, right? It's going, I'm here, now I'm here, now I'm here, now I'm here, right? It's shared between the nitrogen and the oxygen, in fact. And what that does is that it makes it unavailable. So that lone pair is unavailable. So that's the explanation, okay? So that is why amides are not bases, even though they have a nitrogen. If I had a nickel for every time an organic chemistry student just saw nitrogen and just automatically assumed it was basic, I would probably have like $40 or something by now, okay? So don't just make that assumption. There is an exception, and the exception is amides. So the they is amides. Amides are not bases, even though they have a nitrogen atom, okay? It's not the only prerequisite. The lone pair has to be available, and it's not available on an amide. And you're like, oh, Mr. Deon, you spent an awful lot of time talking about that. I did, and there's a good reason for that, is because you have to understand what's going on right here in order for you to completely understand what goes on in chapters 18 and 19, okay? In order for us to completely and fully understand chapters 18 and 19, you have to grasp this concept that I have inside that yellow box. All right, let's move on. So amide hydrogen bonding. Excuse me. It says here the strong intermolecular hydrogen bonding between the nitrogen-hydrogen bond of one amide and the carbonyl of another. So here, I'll just circle some the amides in yellow. So here's one amide. Here's another amide. Okay, here's another amide. Here's another one here. And what do you see is that we see all kinds of interesting hydrogen bonding taking place here. And the hydrogen bond between a hydrogen that's attached to the nitrogen with the lone pair on the oxygen of a carbonyl. Okay, and we see that here, and we see that here, and we could draw, we could even draw in another amide if we want to. Let me get a different pen out here and I'll practice. So if I draw another amide, I'll just draw something similar to what they have. So I'll put an R group. So we have a carbonyl and then an R group. Okay, I could draw a hydrogen bond like this. Okay, so it says here that amides, although they have very high boiling points, simple amides are going to be quite soluble in water because they can also hydrogen bond with H2O. Let me draw a water molecule. Why couldn't this happen, right? This is a polar bond. Okay, so there's no reason why I can't have hydrogen bonding between this hydrogen, my hydrogen on my water, and this oxygen, right? This is delta plus, this is delta minus. Okay, so amides are really interesting in that they can hydrogen bond in a pure sample, and they can hydrogen bond with water, even though they have quite high boiling points. Let's talk about the nomenclature of amides. And I already taught you the difference between a primary, a secondary, and a tertiary amide. In case you've forgotten, I'll go over it again. So if we have an NH2 on the end of our amide, we call that a primary amide. If I have one R group on my nitrogen and one hydrogen, I call that a secondary amide. And you can probably see where I'm going. If I have two R groups attached to my nitrogen, then that is called a tertiary amide. Okay, so primary, tertiary, and secondary amide. Now it says here that the names of amides are derived from the carboxylic acid. So what does that mean? Organic chemistry is a beautiful thing. What do you mean? What I mean is that as long as you follow the nomenclature in chapter 14 for carboxylic acids, that's going to help you a ton in the nomenclature here. If you mastered that, you're going to find naming amides not all that bad. So what we do is whatever IUPAC name, okay, if we had an IUPAC name that ended in oic acid, we removed the oic acid and we placed it with amide. So think about it. Methanoic acid would be methanamide. Okay? Ethanoic acid, ethanamide. Propanoic acid, propanamide. Butanoic acid, butanamide. Pentanoic acid, pentanamide. Hexanoic acid, hexanamide. Okay, you get the point? Right? So then if we have nitrogen substituents, meaning if we have secondary or tertiary amines, then we name the substituent and we do the same thing that we did in amines, and that we prefix it with the capital letter N. You don't have to italicize it if you're writing it out by hand, but normally when it's typed out, it's normally italicized. So let's take a look at these examples that are shown down here. Look, if I was to ask you to name this carboxylic acid, okay, I said, give me the IUPAC name for this carboxylic acid. You would call it ethanoic acid. Okay, and we replace oic acid with amide. I should have pointed out up here, I forgot to do it, and it's not in my notes, so let me just write it in here, and I'm going to kind of squeeze this in. If you're doing it with common nomenclature, you replace ic acid, okay, ic acid with amide. Okay, so let's go back down here. And if I said to anybody in the class, if I said, I want you to give me the common name of this carboxylic acid, okay, give me its common name, you would say acetic acid, so we replace ic acid with amide. So acetamide. Some people call it acetamide, I don't care. As long as I understand what you're saying and it makes sense, that's good enough for me. Same thing follows here. We have propanoic acid. We replace oic acid with amide. So we get propanamide. And again, that's the IUPAC name, IUPAC. And for common, it's propionic acid. So we replace ic acid with amide, so propionamide. So we'll put common over here. Now both of these examples, these are primary amides. Now we get a little bit spicier down here in that we have a couple of secondary amides. So these are both secondary amides. Now, if I showed you, and we just looked at this 10 seconds ago, if I showed you this carboxylic acid, right, you would call that propanoic acid, right? Here it is, propanoic acid. Okay, well, if I have propionamide, okay, fine. So this is the propionamide portion. Now I've got a methyl group, but remember, we call it N-methyl, N-methyl. So this one would become N-methyl propanamide. All right, same thing follows over here. We start with the carboxylic acid portion, or the part with the carbonyl, and this has 1, 2, 3, 4, 5, 6 carbons. So this would be hexanoic acid. We replace oic acid with amide, so it becomes hexanamide, right, which is shown right here, hexanamide. And then I have a propyl, right? This is a good old propyl group. It's like we're back in class, the first or second class, right? Propyl, methyl, ethyl, isopropyl, butyl, sec-butyl. Remember all that? Yeah, so I have a propyl group, so this would be N-propyl hexanamide. And look, this is one of the most beautiful things about organic chemistry. You can take something that you learned in a previous chapter, carboxylic acid nomenclature. You're like, wow, I spent a lot of time memorizing those common names of, formic acid, acetic acid, propionic, butyric, valeric. The good news is you can use them all over again in this chapter, okay? So we have to know common name nomenclature for amides as well, and that is all covered on this table right here. So if you need, to make flashcards or something to help you, these are just the simple amides or primary. These are just primary amides, right? If we were to write out the carboxylic acid, if we had, this carboxylic acid, the IUPAC name would be methanoic acid. Look, methanamide. The common name would be formic acid. Look, formamide. Okay? Ethanoic acid makes ethanamide and acetamide or acetamide. What else? Propanoic acid, propanamide. Propionic acid, propionamide, right? And then we have a couple other just different examples down here of other secondary amides. So if I take my formamide or my methanamide molecule and I add a methyl group to it, I get N-methyl methanamide, that's IUPAC, or N-methyl formamide, that's common. I'm really hoping and praying that by now you've seen the common names of the carboxylic acids by now that you're just so sick of them and that you could, recite them in your sleep kind of thing. Okay, let's move on from there and talk about, we spent a lot of time talking about amides. How do I make one? Okay, you said amides are so great and they're so important and they're found in a few drugs. Okay, how would I make one? Well, there's some really interesting ways to make amides, but we're going to talk about one of the earliest ways that was ever developed to produce amides. And this is a really interesting reaction, but you got to hang on to your hat and try to pay attention because it's one of the few times in this course when stoichiometry gets really interesting. Right? You guys remember stoichiometry from Introduction to Chemistry? Things like limiting reactants and balancing equations. If you think about every reaction, virtually every reaction that we've looked at in this class, the ratio of reactants has always been, 1-to-1. Okay, I add 1 carboxylic acid and 1 alcohol, and I make an ester. Okay, this is one example where it says that we need 2 molar equivalents of something. So let me show you how this works. It says at the top that primary and secondary amines will react with acid chlorides. You guys remember the acid chloride, this guy down here, or the acyl chloride sometimes, or acid anhydrides, and we'll look at this on another slide, to produce amides. But what's interesting is that you need 2 molar equivalents of the nitrogen source to do the reaction, and we call these acyl group transfers because this portion of the acid chloride, this is called the acyl group. I think I might have even asked that on an exam, but just in case you've forgotten, we'll write it out here as well. This is an acyl group. And think about it, what are you doing? When you make this amide right here, you're transferring this acyl group onto the amine to produce an amide. Okay, that's what we're doing. But I want to get into the nuts and bolts about why you need the 2 molecules of ammonia for every 1 molecule of the acid chloride. So let's pay attention to this very carefully, right? The ratio is 1-to-2, right? Because we have no coefficient here, so that means there's only 1 acid chloride plus 2 molecules of ammonia or a primary or secondary amine. Okay, gives us 1 molecule of amide and this interesting fellow here, ammonium chloride. All right. So let's see here. Is there room for me to show you? Oh, good gravy. Probably not. Okay, there's 2 ways you can do this. Okay, you can either just plainly memorize it, and I'll be frank with you, probably a lot of my students have done that, and I don't have any problem with that whatsoever. But in the since there's not a lot of room on any of these slides, and when I was teaching face-to-face, I probably just used the chalkboard. Let me show you quickly, okay? And it will be on video, so you'll be able to watch it over and over. But let me show you exactly what happens. I'm going to go a little bit above the, what's the word I'm looking for? Above the level of this class, okay? I'm going to kind of step into organic chemistry 1, like organic chemistry if you want to go to medical school. But trust me, it will help you understand it. So look, you take your acid chloride, okay? There's a dipole in that acid chloride, okay? So that means there's a partial positive charge on the carbon and a partial negative charge on the oxygen. Now I'm going to delete this part here. I just want you to think in terms of positive and negative. And we're going to add 1 molecule of ammonia to this. Can anybody remind me, is ammonia an acid or a base? Not a trick question. Is ammonia an acid or a base? Yeah, absolutely. It's a base. Okay? Thank you, everybody. That's perfect. So what's going to happen is the lone pair on that nitrogen is literally going to attack and hit this chlorine because electrons have a negative charge, and they're going to hit that carbon. I said chlorine, I meant carbon. They're going to hit that carbon so fast that it's actually going to cause the chlorine atom to leave. Okay? So then what you would end up with is something that looks like this, where we have a carbon and a nitrogen with 3 bonds to hydrogen, and we have a chloride. Okay, a chloride has a negative charge, and nitrogen, when it has 4 bonds and no lone pair, has a positive charge. Now this is not an amide, right? I'll even write it out here, not an amide. You're like, I know, okay? Cool, that's fine. So what happens is the second molecule of ammonia, right, acts as a base, okay? And it ends up taking this proton and putting those electrons onto the nitrogen like this, so that you end up with what? You end up with your carbonyl group and your nitrogen with only 2 hydrogens. Anybody recognize this? It's an amide, okay? Then what else are you left over with? You're left over with chloride and NH3 plus a hydrogen, which gives you NH4 plus. So you're left over with, you're left over with NH4 plus, which is ammonium, and chloride. There you go. So that's what happens in that reaction. It's very rare for me to walk through the flow of electrons of what happens in any reactions that we look at in this class, but this is one case where I feel like it's important to do it in order for my students to understand why do we need 2 molecules of ammonia. If you just want to memorize what's in the green box, okay, it's going to get you where you want to go. It's going to get you where you want to go in Chemistry 102. And if you want to write the HESI exam, or if you want to try to get into dental hygiene or something, it will get you where you want to go. I just want, I want you to understand sometimes that, things are a little bit more complicated than what we look at in this class. And sometimes it just makes it easier. Sometimes students have actually come up to me and said, that actually makes it simpler now that I can see what the heck is actually going on, okay? Instead of just pure memorization, sometimes it's easier to just know. All right, here's an example of amide formation. So this is a reaction that any one of you could do in the lab very easily. Acid chlorides can be purchased from chemical suppliers. They're not very expensive. They are reactive, so you have to handle them with care. But, right, you don't throw them in water or anything. But anyhow, you take butanoyl chloride and you treat it with 2 molecules of methanamine, right? You mix it, you stir it up, and you would end up producing a beautiful amide, N-methyl butanamide. And you also get this salt. But what's cool about this is that it's salts are water soluble. So you can actually separate this from the amide just based off of water solubility. All right. It also says that amides can be formed from an acid anhydride and ammonia. And we looked at the anhydride earlier on in this class. So the anhydride in this case, you can either use an anhydride, right? We looked at acid chlorides thus far, but an acid anhydride will work the exact same way as the acid chloride. You need 2 molecules of the amine or ammonia to make your amide. But this time, instead of getting ammonium chloride, you get ammonium in your negative ion, right? When you used an acid chloride, it was chloride. Now you get a carboxylate. So carboxylic acid salt, or you can sometimes call this a carboxylate salt. Carboxylate salt. All right. What else? There's an amide bond in artificial sweeteners. Here's aspartame. I'm sure everybody here's consumed aspartame at some point in their life if you've ever had diet soda, or delicious Coke Zero or something. So when you get an email from an aunt or something who says aspartame is going to kill you, you just say, well, aspartame is actually made up of 2 amino acids which are found in the human body. So, if you hydrolyze, if you break apart aspartame, you just get 2 amino acids. So maybe you'll build some more muscle. Anyway, the only deleterious effect I can see that you could get from aspartame is some people are unable to metabolize phenylalanine because of a disease known as phenylketonuria. Anyhow, you could look that up if you have some spare time. And then we have neotame, which is another artificial sweetener, which is made from phenylalanine and a modified aspartic acid molecule. There you go. So you see an amide bond in aspartame and an amide bond in neotame, which I think is NutraSweet. Anyhow, let's move on from there and talk about how do we, one of the recurring themes in organic chemistry is once you learn how to make something, you got to learn how to tear it apart, right? You learned esterification, the formation of an ester. Then we learned the hydrolysis of an ester in acid and in base. So now that we know how to make an amide, we have to learn how to blow it to smithereens. And there's 2 ways that we can hydrolyze or break apart an amide. We can either break that amide apart with acid or with base. One or the other can be used. So what happens is when you take an amide and you treat it with a base, with an acid, like a strong acid like hydronium, you break the amide bond. Now, I told you earlier which bond is the amide bond. So here we go. You're like, amides have lots of bonds. Well, they have a few. But the amide bond is this bond in particular. Okay, this is the amide bond. So when you treat an amide with acid, you break this bond right here. Maybe I could highlight it in a better color than green. You break this bond right here. And since you're in an acid, you produce an acid. think about it. If you're an acid, you're not going to make a base, right? So when you treat an amide with a strong acid, you make the carboxylic acid of the acyl portion, and the basic portion, the amine portion, becomes an alkyl ammonium, right? Because when you take an amine and you put it in acid, H3O plus, any kind of acid, could be hydrochloric acid, you're going to protonate it, right? This is something that we looked at earlier when I gave you the whole talk about cocaine, okay, and crack, okay? So we end up with an alkyl ammonium. Similarly, when we take a base and we hydrolyze an amine, we break the amide bond, okay? But since we're in base, if we're in base, we're not going to make an acid. We're going to make a carboxylic acid salt, which is also a type of base. It's a very weak base, but it is still a base. But an amine or ammonia, that's a base. So, you know, when I teach full-year organic chemistry, they use a different textbook. And in that textbook, the author, his name is David Klein. He says this all the time in the book. He always says, if you're doing a reaction in acid, you shouldn't be drawing any strong bases in there as products, right? Think about it. If you're an acid, why would you have a base? Similarly, if you're doing a reaction in base, don't be drawing any products that are acid, right? It's not going to exist, okay? And that's the same thing that we see here. So again, I'm repeating myself. When you hydrolyze an amide, you break this bond in base, right? Sodium hydroxide is a very strong base. You end up with a carboxylic acid salt or a carboxylate salt and an amine or ammonia, okay? Let me just remind you that a carboxylic acid salt is the exact same thing as saying carboxylate salt. They're synonymous, okay? They mean the exact same thing. Okay, let's move on from there. We can go over this part kind of quickly because this is a preview of what you're going to see in chapter 18. So something to look forward to. Everybody needs something to look forward to. For some people, it's a vacation. For organic chemistry students, it's a new chapter. It says a protein, and nowadays, you know, with the new diets and everything, people are always talking about high protein. So we're going to talk all about proteins, and proteins are nothing more than polymers. You're like, I thought a polymer was like a garbage bag, a piece of plastic, you know? That's true, but a protein is a natural polymer made of amino acids linked together by what? Amide bonds. So you think about people say, oh, polymers are dangerous, you know, they're bad for the ocean. Well, I guess they are in some regard, but you could say, well, there's, you know, human beings are filled with polymers because a protein or an enzyme is a polymer made up of amino acids put together by amide bonds. The amino group and the carboxyl group, as the amino group and the carboxyl group come together or link, you end up losing a water molecule. So here's the peptide bond. You know, if I could give one message to you right now, it's that the peptide bond and amide bond mean the exact same thing, okay? So organic chemists love to use a variety of terms to describe the same thing. I don't know why, you guys, just to sound smart, I suppose. But if I say a peptide bond, I mean an amide bond, okay? Usually we mean an amide bond found in a peptide, but I'm not kidding, and you're going to be like, oh, come on, organic chemistry is so frustrating sometimes. Sometimes when an organic chemist, when she or he is not talking about peptides whatsoever, we will still call an amide bond a peptide bond. I know, it's kind of annoying, but that's the way things are in OChem sometimes. Protein synthesis uses tRNA. How about, I don't ask you anything about that on the next exam. An amino acid and protein. So we'll just say, I'm going to write here, since you all always want to know what's important, and you deserve to know that, absolutely, and I'm not being sarcastic at all. We'll say skip this slide. Skip this slide. Don't stress about it. Okay? Where was I? This slide, don't skip, okay? Amino acids and proteins. An alpha amino acid is a carboxylic acid with an amino group on the carbon alpha to the carboxylic acid. Let me show you what that means exactly, and you probably have it figured out already. So if you have a carboxylic acid, right, remember we talked about common nomenclature. We said that this carbon, let's say we have, I don't know, something, anyhow, let's just say This is the alpha carbon. Remember that alpha, beta, gamma, delta thing? Well, remember the carbon right next to the carbonyl carbon was the alpha carbon? So alpha amino acid, the alpha amino comes from the fact that you've got an amine, an NH2 group attached to that alpha carbon, okay? So an alpha amino acid is a carboxylic acid with an amino group, alpha to the carboxylic acid. The alpha carbon also has an R group side chain, except for glycine, which has 2 hydrogen atoms. So if I have this molecule here, if I have a CH2 here, which I do, this is called glycine. Okay, that's an amino acid that is found in every one of our bodies. But if I have an amino acid that looks something like this, I'm going to draw the same thing. The only difference is I'm going to have 1 hydrogen and 1 R group. And if that R group is a methyl group, that's called alanine. If it's an isopropyl group, it's called valine. If it's a benzyl group, it's called tyrosine. It's called phenylalanine. If it's a CH2 with an aromatic ring and an alcohol, then it's called tyrosine. Anyhow, you don't have to have the amino acids memorized at all. Okay, that's not my point. My point is that usually the way I explain this to my students, which makes them look at me funny, is that, you know, if you think about all the people that are online right now, if you look at our DNA, right, we share a lot more in common than we have, than our differences between us, right? Human beings are all very similar. But we all have something that makes us unique. And I'd say, you know what makes us unique is maybe our personality. Okay, personalities make us unique. Well, the R group of an amino acid is what gives them their personality. Okay, there are only 20 naturally occurring amino acids. Generally speaking, there are exceptions to that, but 20 naturally occurring amino acids, and they all have different R groups. Now, you might be wondering, what's the difference between this amino acid and this amino acid here? Well, it's pretty clear that the one in the bigger circle, the one in the middle, has 2 charges on it. And I bet you some of you have figured out why this happens. And the reason why is because here you have a base, because an amine is a base, and here you have an acid. So what's going to happen is the acid is going to donate this proton to the base to give you this structure right here, which we call a Zwitter ion. And that's why amino acids are very commonly drawn, like is shown here inside this green box, in that we show 2 charges that cancel each other out. But we say, well, we have a carboxylic acid and an amine, which is a base, and therefore the base is going to take the proton from the acid. All right. Neurotransmitters carry signals from a nerve cell to a target. They can be excitatory or inhibitory, and they all contain nitrogens. A type of neurotransmitter synthesized from the amino acid tyrosine, which I mentioned earlier on. I can draw the structure of tyrosine here for you if it helps you out, which it probably will. And I'll draw it as an uncharged molecule. This is tyrosine. I always tell my students you can memorize it because it looks like a tire swing. Tyrosine, tire swing. Anyhow, if you have a deficiency in dopamine, which is derived from tyrosine, and we'll take a look at that in a second, you can end up with Parkinson's disease. But if you have too much dopamine, you can it's associated with schizophrenia. Anyhow, this is the pathway of what's called catecholamine synthesis. So going from the amino acid tyrosine, and then you go through L-DOPA and dopamine and norepinephrine, and then finally down here to epinephrine. Anyhow, I'm not sure what I would ask you about that really at this point. So let's just move on from there. Serotonin is a neurotransmitter that's made from a different amino acid called tryptophan. So tryptophan, and the structure of tryptophan is shown on this slide. It's shown down here. So tryptophan, you add a hydroxyl to the indole. So here's the hydroxyl that you add to it. And then you modify this by what's called a decarboxylation to make serotonin, which again is a neurotransmitter. Deficiencies are associated with depression, and it could be involved with carbohydrate cravings and can affect all kinds of different things in the body, including pain perception, thermoregulation, and sleep. And then histamine is also another another neurotransmitter, and it is derived from the amino acid histidine. So histidine is a naturally occurring amino acid. I'll put that on here, amino acid. So really, I'm thinking about this while I'm talking to you about it. All I would expect you to know is the names of these neurotransmitters. Acetylcholine is another neurotransmitter that is derived from the molecule choline. Choline. And we saw the structure of choline earlier on. In fact, it's right here. And that pretty much takes us to the end. So glycine and aminobutyric acid. Let's see here. Removal of a carboxyl group from glutamate, which is another amino acid, produces gamma aminobutyric acid. Anyhow, there we go. And really that takes us to the end. Amines and amides. Yeah, the main thing is knowing the nomenclature and the equations. And then as far as neurotransmitters goes, I would never ask you to memorize the structure of all those neurotransmitters. So just knowing the names of them is good enough, okay? But what we really need to focus on in this chapter are the equations, the chemical reactions that we looked at, because we spent a lot of time on those. And there you go. That pretty much brings us to the end of this chapter. Somebody asked me about practice problems, and I will post a list of practice problems for chapter 15 as soon as possible.